I am Meg White. I'm a freshwater scientist with the Nature Conservancy, and I'm going to take you in the next 20 minutes a little bit of a tour of an evolution of a project. It continues to evolve. There were a group of us that were interested in understanding how tributary junctions might serve as a source of dynamism, particularly on regulated rivers, and how that could translate to information and tools for conservation practitioners. It was the brainchild largely of Pat Shafroth and John Sanderson and THIESSEN, and it's been funded through DOR, Water Smarts, Southern Rockies Landscape Conservation Cooperative for the last couple of years. So we're still very much in the throes with this work. Next slide, please. Okay, so first and foremost, we need to talk about habitat complexity, and specifically our group is interested in riparian habitat complexity. There's been a lot of work that's been done, and there's sort of a state of knowledge about aquatic habitat complexity. What that means for the riparian component of the ecosystem still remains to be seen. So these were some of the specific points that we wanted to focus on. Obviously, with defining peak flows and regulated systems, it's possible, certainly based on the number of field observations that have been made by my colleagues, in particular, with some of my own too, for the Dolores River, that tributaries may in fact serve as a source of dynamism downstream from the point of regulation, and that may also serve as an interesting data point, an obvious place to start looking to participate in riparian restoration outcomes. So the thing that we wanted to focus on with this particular research is that tributary junctions again may provide both a diverse geomorphic complexity within which then riparian cover may have refused to surface, and then also that there's very little that's been known about this. There's been very little research on habitat complexity from the terrestrial lens, particularly with tributaries as the source of dynamism. Next slide. Okay, so two specific research questions that we were attempting to answer. The first was focused on patterns, and the second was focused on process. And our spatial scale was quite large for this. We were looking at both the Dolores and the Colorado rivers. And we'll show you the study site on the next slide. So the first question that we asked was investigating patterns in riparian and channel habitat complexity at those tributary junctions along these regulated regions. And specifically, what we wanted to know, does riparian habitat diversity change with tributaries? And is there some sort of pattern that happens then as you increase your distance from the river? So with this particular analysis, we included all tributaries. The second question then was more focused on process. It was saying, okay, if there are changes, or where we do see change, what are those drivers of change? What are some of those characteristics of the tributaries that tend to be the drivers of the most significant inputs to this? With these, of course, we made a couple of hypotheses that are stated up here. We chose 3 specific tributary characteristics that I'll get into a little bit more in a minute. Again, the idea here was to develop a tool that practitioners can use for more passive approaches or more informed approaches to riparian restoration from a number of yes. Sorry. These are our 2 study sites. The Colorado River, there were about 70 tributaries on this section of the Colorado River from the Utah border down to the confluence with the Green. And then and that was from McPhee Reservoir all the way to the confluence with the Colorado. 103 tributaries were included for the initial question on the Dolores, and some of these were excluded in the second part of our study. Next slide, please. Great. Good. Thank you. So part of what happened with our VEG classification, with our approach to this, is that as opposed to hand digitizing, use some new approaches in both remote sensing and sort of spatial analysis. So we used a supervised image classification, which was a great opportunity for us to test a relatively new method. And the supervised image classification was fairly successful. It was as successful as the literature. We have an accuracy of about 75 and 76% on each river for each of these classifications. And you can see the classifications of the different both vegetation types and then the channel types, which I'll talk about in just a second. Now, the supervised image classification was successful at that 75 and 76% accuracy for the vegetation types. However, we found that that wasn't the case with the channel types and the level of resolution that we were attempting to capture there. So we also did the supervised image classification for the entire bottomlands, and then we ended up doing analysis on a number of different scales across the bottom. With the channel types, and you'll see again if I go back to this slide, there are 5 types. I couldn't find an image that was as well. The isolated pools in particular were very small and tended to be pretty far out on the floodplain. So these were the main channel classification types, and we found that we had to hand digitize the channels. So this was because trying to tell the computer what kinds of color spectrums to recognize in the supervised image classification was difficult given the turbidity of the sediment flow and the variation across the water types, even in these different categories. So it was easier to do this by hand. When we ran an accuracy assessment on the hand digitized versus the supervised image classification, we were relieved to find out that they were relatively similar. So it wasn't that we were really trading off. It was also an opportunity for us to, again, test a relatively new technique. In order for us to understand what was happening along an entire reach of river, we had to figure out how to assign spatial locations to the tributaries. And so we ended up using THIESSEN polygons. And we assigned THIESSEN polygons at 4 different scales, but found one of those scales to be relatively useless in terms of this pattern. 3 that we're reporting on are 10-meter slices of the river, 25-meter slices of the river, and then 100 of the river. So imagine this is how we're binning the patterns that we're seeing as we move upstream and downstream from the tributary in this situation. So the THIESSEN polygon, again, it just defines an area of influence, and it gives us an opportunity to measure distance from the nearest tributary. The one thing that I want to emphasize with this is that it's really been an exploratory analysis. So we went in thinking that the patterns were really going to emerge pretty strongly with this work, given what we've seen in the field and just sort of the nature of rivers and tributaries, particularly in regulated systems. And so we ended up looking at distance from the river. So we had different lateral scales that we looked at. We did the full bottomland, we did a near channel area, and we also did the channel area. So just looking within the channel because we had so much trouble classifying that. Then we also did a number of different THIESSEN polygons, a number of different spatial scales along the river, so longitudinally. And then finally, we wanted to see if we could isolate trib effects. So we wanted to see if the patterns changed when you included all the tributaries that we had. If we did a 1 kilometer buffer, so 500 meters upstream and downstream, and a 2 kilometer buffer, 1,000 meters upstream and downstream. Both to capture the influence of an individual trib, but also to try to put some bounds on the actual effects of that trib that we were seeing or not seeing. So again, for both rivers, and in each one of these cases, we had 4 main response variables. We looked at veg class cover, which was presented a couple of slides ago. We looked at those 5 different channel types. We looked at bare ground, and we looked at tall woody cover. So I'm going to go briefly into the hundreds of box plots that we've generated for this. I will go quickly. I think the best way to look at this is that immediately you can see, first and foremost, the y-axis. So I apologize for that, the y-axis for now. If you look at the median lines on this, you can start to see some pretty general trends, especially within the first 150 to maybe 300 meters, depending on what we're looking at, of the tributaries. Now, the way to understand this is that on the x-axis, these are the different distance categories. These are the bigs. So there's an N for each one of these. So this is the entire river, and you have how many tributaries, or how many THIESSEN polygons are falling within 50 meters of a tributary, within 51 to 100 meters of a tributary, so on and so forth. So read it that way. That's what the box plot is showing you. And this is showing you the differences between the Colorado and the Dolores. Again, not a lot of strong trends that are surfacing here, which was surprising to our group. What you can see with the cover classes is that there is a slight increase in cover class on the Colorado as you move towards the 150 mark. But again, this sort of served as fodder for us to dive deeper. The channel types, again, this is across the 3 different THIESSEN polygons. We were starting to see, we wanted to do the same thing with the channel types because we knew the geomorphology and the veg were so tightly bound. You can see that as you move further away from a tributary, that on the Colorado, there's a little bit of a trend of a decline in channel types. Same on the Dolores, especially at the smaller scales. When you get over to the 100-meter zone, so there's something left to be desired with this particular method or approach. So what we did from there then was to dive a little bit deeper and look at individual responses and to play with the scale a little bit more. So these are some results for the Colorado on the left and the Dolores on the right. For the near channel data grounds, and what we found was that in near channel environments, we could read relatively well for the 25 meter scale. But there was this interesting drop that happened, drop off that happens at where those red circles are, at about 300 to 350 meters downstream. So again, these are points for us to start to dive a little bit deeper. This is very much still a work in progress. And has ended up becoming more of a methodological approach. For the tall woody cover, we found there wasn't enough cottonwood in these reaches for us to really be able to do anything in the channel. It's less than 3%. There's really not a lot of cottonwood in the entire bottom line. If we're going to try to look at trends for cottonwood, we're going to have to, in the tall woody category, we're going to have to look across the entire bottom line. So again, those same distance categories, and we've got a declining trend as you move further away from the tributary. So that tells us something. Again, none of these are statistically significant. It doesn't mean they're not ecologically significant. They give us information as to how to move forward. And then finally, the channel types. This is again Colorado and Dolores. This is the 100-meter increment, and this is the 2-kilometer isolated trib. What you can see here is really where you want to look for those first 100 meters or those first 2 bins. There tends to be a pretty significant drop. So we thought, well, what does that mean? Does that mean that we need to narrow our spatial scale to understand what's going on? It's never very much fun as a scientist to not get a ton of really resounding results in a research project, but at the same time, it's offered up a whole bunch of questions and nuances as to how we should pursue or what we can do to inform this work moving forward. And then terrestrial cover types. What you're going to see if you look at this trend, you've got really high channel complexity close to the trib, and then you've got lower veg cover, lower veg types or density, and then it increases as you move further downstream. So there seems to be a relationship between those two that's counter, and that's one of the things that we kind of want to dive into a little bit more. So the first point that we want to make in sort of these preliminary results and conclusions is that scale matters. It matters how we're looking at these. It matters how far laterally we're moving out into the floodplain. It matters how we're choosing to use these THIESSEN polygons to bend and create spatial scale. And then finally, the cover complexity and the channel type complexity, they seem to have differing relationships. We thought that they would both increase and then decline with increasing distance initially, and what we're finding is that channel complexity is higher at the tributaries, at some tributaries, and then the veg cover increases as we move further away. So that disturbance factor becomes a big one. most of the trends that we're seeing are falling within a 500-meter zone of the tributaries. So from here, we of course wanted to dive into the second question. And that second question is, okay, if you're seeing changes at these tributaries, what's driving those changes? What's potentially causing those? So we started with a change point analysis. The change point analysis, again, was we did not run all the tributaries on the change point analysis. There was some error in the NHD data. So we removed any of those NHD files that were, or the tribs that were corrupt. Some of them were non-existent, or some of them jumped watershed boundaries. It was really interesting to see. We also didn't include the larger tribs or the outliers because they caused too much noise in the data. So we didn't include the Dolores into the Colorado, we didn't include the San Miguel into the Dolores. So this change point analysis, the green points are points where tribs enter into a system, and the red points are where there's change detected. And any one of those response variables. So veg cover, channel types, so on and so forth. This is a screen capture of just one of those. What we found with this was that there were some change points, but our N was really low, and I'll talk about that in just a second. So the three characteristics, the three driver variables that we became very interested in. So we tested out several, but these were sort of the three that we landed on. Were watershed size or watershed area, the slope of the trib, and then the slope of the main stem, immediately upstream and downstream. So we're finding that what the main stem is doing, the receiving system, tends to be a more important factor than we thought. We were also trying to do the slope of the trib mouth to the slope of the main stem, but the data were too blurry for us to actually really be able to dive into that. So these were the three big variables that we have our elbows in right now and we're actively working on. With the change point analysis, what we found, and the change point analysis was great in identifying from a really large spatial scale and sort of a statistical way of saying what tribs are showing up as significant. Unfortunately, we only had about 8 or 9 tribs that really showed up as significant for a number of the different variables. So what we're doing then is diving into those almost like a case study perspective. So because our N is so low, we are looking at these three variables and saying, what can we do next? What can this study set us up to answer for the next part of this? Because clearly our spatial scales, we're looking at this huge river segments, and our spatial scales aren't lending themselves to answering the questions at the scale that we're looking. Top to Colorado, for a couple of those response variables, the bottom part of this table is the Dolores, just some basic descriptive statistics that we found. So, for example, for the Colorado, there was 1 tributary change point that had cover class density. There was 5, the channel class density that showed up as being significant. Of those, then we were able to see what the median watershed size was, which is the asterisk means, and what percentile it falls into. That's the parenthesis. Same thing for the tributary slope in the main stem. So that's how you read the table. And we're very much in the throes of interpreting this, playing with some of the data similar, and seeing what other kinds of patterns we can pull out from this information. The sort of preliminary results that I will go through in the next steps is that we are working from these box plots to try to find some general trends and just pull some lessons learned from this. We're approaching individual tribs again as a case study, and the initial results is that we see different response patterns at different scales with different variables per river. It's that one size fits all doesn't necessarily work, which is somewhat surprising in this particular case, except that the 2 rivers that we're looking at are significantly different in their own size. We want to focus more on the main stem characteristics and narrow the scope to dive deeper, to be able to really understand what's happening with this trib mouths. One of the things that we wanted to do was really be able to tell the story of what is the extent of influence of a trib. So in my ideal world, we would have these bins of these trib types or characteristics that would then say, we've got a watershed area of type A, you're going to see an influence in this river upstream and downstream of this distance. We're not necessarily seeing those patterns yet that will let us tell that story.
I'm wondering if you have done anything looking at the relative size of watersheds of tributaries to the main stems. Like I would think, a watershed of size X would have a lot more influence up higher in the river than down low.
Yeah, we talked about that. We were trying to figure out how to do that, particularly on a system like the Colorado, since we were only looking at a section of the Colorado. What do you use as your denominator in that particular situation? So we absolutely talked about that and talked about the spatial locations of the watersheds along our study reaches, and frankly couldn't quite figure out how to do it because we were only looking at a section of the river. So how do you create a denominator for the Colorado in particular? But that was one of the first places we started, which was why we knew to keep the green out of the whole mess. We originally had extended our study area.
Hi, Meg. Have you had a chance to look at the sediment characteristics of the tributary watersheds and how that might influence?
We want to. I think that we weren't able to do it in this study. We thought about trying to use a GIS layer and figure out how to put roadability in here. And there were so many moving parts. Keep your science simple, people. That we just weren't able to actually get there, but it's definitely one thing that we need to look at. Absolutely. It's something that we have to acknowledge in this write-up.
All right. Next up, we've got Matt Grabeau from the Sonoran Institute, and he will be discussing modeling shallow groundwater for support of riparian areas. All right. Thanks, Matt.